All right, let's go over two things here. We're going to go over inverse trig functions and the composition of inverse trig functions, which is this little weird notation that you see here. And so before we begin though, let's cover some basics of where inverse functions came from, because in this video, you'll realize that this chart becomes pretty important. So going back to figuring out where inverse functions or how they're derived and how they're restricted, it really comes from, in this particular case, we're going to be talking about cosine, but you'll see that there's one for tangent and sine itself. So in order to take the inverse of a function, in this case we're talking about cos inverse, we need to make sure that its domain and range are what they should be. So just to cut to the chase here, we're going to need to talk about horizontal line test, because in order for an inverse function to really exist, you must have it pass the horizontal line test. In other words, I know that if we go beyond these 2 points here, it's going to fail. So let me explain. If we do the horizontal line test at any given, y value here, your horizontal line will only pass the graph once, right? Or it'll only cross the graph once. If we exceed the right-hand side, so if we go to the right-hand side a little bit, and even just a little bit to the left, it doesn't matter which one you choose, you'll hit the graph at 2 different points. So that means if we go out of these 2 bounds, 0 to pi, it will fail the horizontal line test. Therefore, we can't really talk about inverse cos past those points. So that's why you'll see that for an inverse function, really what happens is the domain and the range get swapped. So the domain and range become the domain becomes the range, and then the range becomes the domain for the inverse function. So with that being said, if you realize the domain of cos was all real numbers, whereas now for the inverse function it's 0 to pi. But the reason it's 0 to pi is because we can only talk about the inverse function when it passes the horizontal line test. So that's really where it comes from. All right, so just to kind of cut to the chase here, I've provided you with this table of all the range values you really need to think about or have to remember, etc. As we do these problems algebraically, you'll see how we're going to refer to these to the range values of the trig functions as we go on. Okay, so let's get going. So one of the first things you want to do is be able to read this problem. What this problem is really, if you notice it, it looks very similar, but it's kind of backwards now. And that's the whole idea of inverse functions. They're just really your functions backwards because your x and y values swap. What that means is we used to have to solve for this value when we were given some cosine theta. Now we get this value and then we find out the actual theta that belongs to. So theta equals cos inverse of negative radical 3 over 2. Now, you don't always have to write this step, but my suggestion is that you do it until you get it down. Otherwise, you don't really have it down. So with that being said, here's where this table comes into play. If you realize this value is negative in here, right? So it's negative right here, which normally would mean that, hey, we want to talk about these 2 quadrants because that's where cosine is negative, right? But we're no longer talking about cosine. We're talking about inverse cosine. So that's where we need to pay respect to the table, right? To the table right here. Okay, so cosine exists between 0 and pi. So that's where the outputs we care about are. So 0 to pi is here. Therefore, we're talking about this first quadrant and the second. However, making some more educated assumptions here, you realize that this is negative. Therefore, we can't really talk about the first quadrant because all our trig functions are positive. We are in the second quadrant here. So you go back to your basics. You draw a triangle. You put the x and y values that you have, because remember, this still is the same. So that's x over r. And so you fill in the triangle as you see fit. So we have radical 3, 2, and this should be 1. And now if you realize that's actually a 60-degree triangle, right? Sorry, 60 degrees. That's a 30-degree triangle in the second quadrant. So it's 30 degrees reference. This is how you would write that. So it's 30-degree reference, but in the second quadrant. So one of the easiest ways to do that is just subtract 180 from that. So that's the actual value is 150 degrees. Or, which you should always be comfortable with, is you write it as radian, right? So we're going to have theta is equal to 5 pi over 6. And there you go. Again, you could write your answer probably in degrees, but almost always you're going to need to use radian, so you should be comfortable with rewriting it if possible. And that's how you do it, right? So quadrants do matter, signs do matter. Most importantly, this is sort of your new table that you need to go by, so you need to keep that with you whenever you're forgetting those ranges. Here, same thing. We do the exact same thing. We are trying to figure out, hey, what theta is going to give us a value of 1 for sine. Now, this one's a little weird because remember that this is not a special triangle, okay? This is your whole little values at 0, 90, etc., etc., etc. So that's 1, 0, 0, 1, blah, blah, blah. So why do we stop there? Because if you realize sine is y over r and y is 1. And so at this point right here, this angle right there, that's where we need to be. So that's simply theta is equal to pi over 2, right? Now, as you notice, we didn't really talk about this table for that one, but you still do need to, right? So inverse sine exists between negative pi over 2 and pi over 2, so that is actually right here. So it's between 0, so one of the ways you want to read this is 0 to pi over 2, and then 0 to negative pi over 2, right? Please do not exceed traveling past this counterclockwise, because you're getting out of bounds here. You want to stay between this range and this range. So again, pi over 2 to negative pi over 2. And this is good, right? Because it does lie between the negative pi over 2 and pi over 2. So this output is possible, right? Okay. All right. So moving on. Again, if we're talking about inverse functions, remember you need to pay respect to that. And you'll see that here shortly. But first, let's start with an easy example. Now, a lot of teachers will give examples or problems that sort of are related to this one. Now, there is a special case where you cannot do this trick, but those problems are not often encountered because the work is a little bit more difficult. But what does that mean? So what that means is, if there's a rule basically that if we have this, okay, so cosine of x, okay, and you could swap these two if you want. The answer to this is really just x, right? Which means it's just whatever this, value is inside your function. And so you're saying, okay, well, my answer is 7 pi over 10. Well, why is it so easy? Well, this goes back to the whole idea of, hey, if we're abiding by these rules, there's a trick that essentially you could cancel out these two functions, right? They're just inverses of each other. So what that means is you can think about cancellation. So you could say, hey, those two things cancel, and my answer is 7 pi over 10. Now, that involved a little bit more shortcut than it did math. But if you have another problem like this, most often, if this isn't your answer, you're going to have to subtract by pi. So it's going to be pi minus 7 pi over 10, and that's going to be your actual answer. But that's not what we're doing in this video. We're not actually going to go over that example because, again, those are considered to be special cases. So if your teacher gives you those types of problems, well, that sucks for you. But let's stick to sort of the basic problems here, okay? Now, these look different, and you kind of solve them differently, but you use the same graph we were using on this other set of examples. So what do I mean by that? Okay, well, in this case, there's not a lot of special triangles that you might get, because the way you do these problems don't necessarily mean or make it easier if you had a special triangle. Hear me out. So for these two, you're gonna really just want to start by graphing, a table or an XY graph like this. And so now what you want to do is two things. Ask yourself first, what quadrant are we in? You should always ask yourself, what quadrant are we in? This is positive for tangent, okay? So what that means is, if we go back to the other side over here, tangent exists between negative pi over 2 to pi over 2, but not including those values. Which means, hey, it's also similar to sine inverse, but it actually does not include the endpoints of negative pi over 2 to pi over 2. So with that being said, tangent will be positive here, so we'll drop the triangle here. And again, you go using the same old rules. So this is 6, this is 7, because it's y over x. And then this is still a hypotenuse, right? So you go back to your basics. You have to do the Pythagorean theorem. So 7 squared plus 6 squared equals, and I didn't work this out beforehand, so I'm going to have to actually do this real quick. So 49, good thing I have a calculator with me. So 49 plus 36. So that's radical 85. Most times you could just leave it as that. There's no need to simplify. And then focus on the trig, right? So don't simplify. I mean, that's just my advice. So with that being said, we should have gotten radical 85 once you do the whole Pythagorean theorem process. So now we have r. And remember, secant is still something that you need to remember. So secant tangent of inverse of 6 over 7. To really solve this, now all you're doing is reading the secant off of this. And remember, secant is r over x. So now all we have to do is say, oh, well, that's just radical 85 over x, which is 7. And that's it. So you build the triangle on a coordinate plane, and then you're just basically putting down your values, solving for any missing sides, and then read the triangle again for the other trig function. With that being said, let me just recap here. Composition functions is not trigonometry. It comes from just algebra, right? So we have to solve inside out. So we're solving this first. This made us draw this little triangle here. And then why do we draw a triangle? Really, if you want to get specific, is because this is theta, right? Think about this, how we used to read it. Secant theta. Now, this isn't a special triangle, but this triangle still formed a little angle right here, right? That's still our theta. So now, using these values here, we wrote 6 over 7. Okay, Pythagorean theorem gave us radical 85. Sorry if I'm wrong, in case that's wrong. But now we're asking to solve secant of theta. So what that means is just read the triangle for secant, which is, again, x over r. And that's how we got the radical 85 over 7. So I hope that made sense. But let's finish this last example. I did this one just to show you because this is a special right triangle. However, it just makes you being able to find the all sides of a triangle much faster. But you still have to follow the same rules. Remember, this is negative. This is inverse cosine. It's between 0 and pi. So it's between 0 and pi. And since it's negative, we're in the second quadrant, right? So we're right here. And we just dropped the values, right? So this is rad 2 over 2. This has to belong to a special right triangle. So that's 1, 1, radical 2. Okay? So again, we don't care about the fact that this is 45 in the second quadrant. Remember, now that we just did this, we solved for this inside. Now we just read the tangent off of that. So the answer is going to be, what is tangent of my graph? And tangent is y over x, which becomes 1 over 1, which is just 1. And that's your answer right there. So this is a little presentation of your typical inverse trig functions that normally people get. There are special cases, but we're not going to cover that for the most part. Most people don't. These are going to be your typical problems that you see. So I hope it helps.